All right, given the advent of 2 snow days, cold days, we're going to try this out. You guys are going to experience my first video. Woohoo! I'm going to try and teach you Solid of Revolution over this. It will probably be like a block day, so there's this to learn with the homework, and that should cover your Wednesday, Thursday, and then Friday we will finish up chapter 7, and hopefully Monday do some review, and I'm thinking Tuesday for a chapter 7 test because we need to keep moving on to get you guys on track for the BC exam. So with that said, we're going to learn the shell method. The shell method isn't explicitly tested on the BC exam, but it is a good method to know as a general help, as well as it makes the DISC method make a little more sense when you have something to compare it to. So that's why I like teaching it, and it's just kind of cool to think about. But we are going to find the volume of a solid of revolution using the shell method. To kind of visualize our shell method, we have, if I have this shape right there, and I want to rotate it around the y-axis, you can kind of see maybe what shape might result from this. I kind of think of it like a bundt cake, right? If I revolved this around the y-axis, you can get a sense of this 3D revolution of an object. But notice that if I'm breaking this up into my lovely little rectangle, and I rotate that whole rectangle around, what I'm creating is this shell thing. So it's a little different than a disc or a washer, right? Washer was more a flat with a circle. This has actually got some depth to it, but it's a thin little shell, right? So we have that whole thing. And then as I add on more shells and rotate those around, you end up with what looks like kind of this graduated cylinder cake thing, where each shell fits inside the other. And so if you make these shells, if you add more and more shells, of course, you could get back to the actual full shape and get a nice, smooth bundt cake that you're looking for and find the volume of your cake. So that's the shell method. And there's some cool GIFs online. If you just type in like shell method GIF gallery, you can find some cool animations where it runs you through that. But the first thing we want to do is be able to find the volume of one of these shells, right? So to do that, here we have an ordinary shell. And we'll start with a rectangle, right? And we're going to revolve that rectangle around its central axis. Our rectangle has a height of h, and it has a width of w, and it sits on an average p away from our axis, right? Since it is a shell, we have this outer radius, and since w is my width, and p kind of sits right in the center, my outer radius is going to be p plus half of w, right? And my inner radius is going to be p minus half of w. Remember that a volume of a cylinder is equal to pi radius squared times height. And from that, we can get the volume of the shell as just the volume of our cylinder, so the outer radius, minus the volume of the hole, which would use the inner radius, right? So putting those two together, we have pi Our outer radius would be p plus half of w squared h minus the volume of the inside is our inner radius, p minus w over 2 squared h. And you might smell some foiling coming up, in which case you are correct. We can take out p and h from both of them and kind of simplify it, but as we expand this, we get p squared plus 2 pw over 2 plus w squared over 4 minus p squared minus 2pw over 2 plus w squared over 4, and then our h on the end over there. And what's nice is these p's cancel because of the negative sign. These w squared over 4's cancel. And then if I have 2pw over 2 plus 2pw over 2, really I end up with 2pw. Right, so that simplifies down quite nicely, and with a little rearranging, we can get 2 pi out front since it's constant. We have a p, we're going to have an h, and our width we're going to put on the end because normally our width is what we want to shrink down, and that becomes our dx or dy, right? So you have 2 pi, you have the average radius of your shell, which is p, you have the average height, or just the height of your shell, and you have the thickness to find the volume of one shell. Now, if we can find one of them, we can find a bunch of them. So if I have this lovely shape and I want to find one shell inside this shape, right? Again, we have w might be our delta y, right? Our p, or our radius from the axis of revolution, is going to be a function, right? So p is actually a function of y. H, how high it is actually a function of y. And so my one shell volume, is going to be 2 pi p of y, h of y, times delta y. And that would be one of them. Now if I want to add on, maybe say, this red cylinder in here, that would put me in a little shell on the inside, right? And so I could add the outer one, plus the inner one, plus the next one, plus the next one, plus the next one, and what I end up with is an addition of all of these shells as my y kind of moves along up the way, right? So I got my first one, my second one, my third one, my fourth one, as delta y is increasing, right? 1, 2, however many I have. So now we have a bunch of them. And if I keep going so that I have, as n approaches infinity, notice this pattern again, this becomes our integral, right? And we're going from c to up to d. These are our functions. Delta y becomes infinitely small into a dy, and 2 pi is constant. And so you have how to find a volume with the shell method. P, again, being the radius from your axis of revolution, and h being the difference between your functions on the right and on the left. And in some ways, this turns out a little bit easier sometimes. Not all the time, but sometimes. So just to see it on 2 different planes, we have our shell method definition. In your book, this would be on page 466. Notice that if I have a horizontal axis of revolution, or it's going around the x-axis, my shell is going to go around it, and it's laying horizontally, right? So it's parallel to my axis of revolution, and my width is going to be in terms of y. So we want our variable to be in y. So if I'm going around x, the variable should be in y, and therefore you have 2 pi c to d p of y, h of y, dy. On the other hand, if I have a vertical axis of revolution, since I'm going around the y-axis, I want to be in x variable. So now I'm rotating around, but my width is delta x, which would become my dx. And so now I'm going from A to B with p of x and h of x. So notice my top minus bottom for h, my right minus left, down for p, or the radius of my shell. So either way we can do it. It's up to you in a lot of ways to draw the rectangle in. If you're parallel to the axis of revolution, you're going to be using a shell method. And we'll see later if you're perpendicular to the axis of revolution, then you're going to be using the disk method. Couple of things. P is always the variable of integration. To the axis of revolution. And I should say the difference. Put the difference in there. And just remember that that's always going to follow the top minus bottom, right minus left rule. So if the axis of revolution is on the right, then that goes first, and it's that minus your variable. So just keep in mind, it's always top minus bottom, right minus left. H is always the difference between your functions. Again, top minus bottom, right minus left rule in play. So let me run through an example for you, and then I'll let you try an example. So we want to find the volume of a solid of revolution by revolving this region around the y-axis. So as you notice, we are parallel with the y-axis. Our width is in x, so we want x variable of integration, right? H is the difference between the functions, so I have my top function, which is x minus x cubed, the bottom function, which is nice, it comes out to being 0. So h is just x minus x cubed, top minus 0, and that works out nicely. P is kind of the tricky one. P follows the bar, and so if I have the bar right here, you know, that might be 0.75. If I have the bar right here, it might be 0.5. If I have the bar here, it might be 0.25. It doesn't matter where I move the bar, it's always going to be where I put it. So that's why we have x. It's just going to be, if it's right here, it's x. If it's right here, it's x. If it's right here, it's x. And so we want it as x minus the axis, don't forget the axis of revolution, which in this case is also 0. So it's really just going to come out to x. And that's generally the case. It might be x minus 2, it might be x minus 5, depending on where your axis is. But you're always just using the variable because that's where your rectangle is kind of sliding along as you're changing with x. So our volume ends up looking like 2 pi from 0 to 1. We have p, which is just x. And we have h, which is x minus x cubed, and we're in the variable x for dx. If you want to pause the video and actually solve that by hand, go for it. It's a good practice. I would start by distributing that out, and then once you unpause the video, you should get 4 pi over 15. So let's see that again, maybe on a different problem. So now we have finding the volume of a solid of revolution formed by revolving this region around the x-axis. So notice since we're doing a horizontal, we want to be in terms of y. Right, and so it's nice they give that to us, x equals e to the negative y squared. I would pause the video, however, and try to find what h of y would be and what p of y would be. Remembering the right minus left, top minus bottom, what would those be? And fill in the volume. Oh, jumped. All right, what would the volume formula be? So I would take a pause right now. And hopefully you found, since it's right minus left, e to the negative y squared minus 0, because that's our stopping point. And then for p, we're just following this height up the way. So it's always going to be y no matter where we go. And so we have y minus 0, which just equals y. And then our volume should end up being, give ourselves a little more room, two pi. We're now in y, so we want to go from 0 up to 1 that way. P is y, h is e to the negative y squared, and we have dy. And that is solvable by hand using a little u substitution. You already have a 2 and a y in there, so it turns out nice. But with that, you should get negative pi e to the negative y squared from 0 to 1. And of course, that leaves you with pi 1 minus 1 over e, or if you're using your calculator, 1.986. So you can see the hardest part is probably just finding what's your radius, in which case it's always your variable that you're working in to the axis of revolution, and what's your height, and your height is just the difference between your top and your bottom, or your right and your left of your function. And once you have those two things, it's 2 pi p times h dy, wherever you're going. Not too bad. To compare the two methods of disk versus shell, notice for our disk method, if I want to go around the y-axis, I'm going to be in terms of y. So y-axis revolution, variable is y. They are the same, right? Versus if I'm going around the y-axis and I'm using a shell, notice that I'm on delta x, so y-axis revolution. Now I'm in variable x. So these are opposite. These are the same. Disk method is the same. Shell method, they're opposite of each other. Same thing goes for if I'm going around x-axis revolution, the variable I'm in is x because it's the same. But if I'm x-axis revolution on the shell, then my variable is in terms of y. Another way to think about it is your rectangular bars. Notice if I'm going around the y-axis on the shell method, my rectangular bar is perpendicular, right? If I'm going around the x-axis, again, my rectangular bar is perpendicular. So bar, the rectangular bar, is perpendicular to your axis of rotation. Or we could say that it's perpendicular Similarly, if we have a y-axis revolution, notice our horizontal bar, or our vertical bar, in this case rectangular bar, is parallel to the axis of revolution. And again, for the y, or the x revolution, our rectangular bar is parallel to our axis of revolution. So our rectangular bar is parallel to axis of revolution. Or a way to remember that is that it's always going to be parashell. I wait all year to make that joke. I'm sorry I can't make it for you in person. So comparing the two, sometimes shell method is preferable, sometimes disk method is preferable. You guys get to choose. Sometimes it's easier if you just want to work with your variable in x always and you have differences in revolution. Well, on your x-axis, if you want to work with variable x, you should use the disk method. If you're doing a y-axis revolution and you want to work with variable x, you should do a shell method. Sometimes one is better than the other if you just draw it out. So in this case, if I drew out this picture for you, we have x squared plus 1, which looks like that. We have x equals 0, x equals 1, and y equals 0. All right, so we have this whole region right there. If I wanted to use the disk method and I'm going around the y-axis, right, disk method, remember, perpendicular, my rectangular bar would be perpendicular to the axis of revolution. But notice as I'm going to run up this way, my r goes from right to left. This is the same, but as soon as I get here, I'm going to need to set up another volume. So you're actually breaking this up in two parts in order to do the disk method. And we can still do it. Since it's on the y-axis, disk method, y-axis means I need to be in variable y. So x would equal y minus 1 square root. And from there we can work with that. Volume is always pi integral of big R squared minus little r squared dy. And since I'm going both of these, the first one would be pi from 0 to 1 on 1 right minus left, so 1 minus 0 squared. And there's no whole to worry about, which is kind of nice. And then I want to add that on to pi from 1 to 2, right? And now I have big R, which is 1 minus 0 axis of revolution squared, plus, let me get rid of that, or minus, sorry, little r, right? And little r is now my function to the axis of revolution, which is 0. So y minus 1 squared dy, running into that. And like, we could do that. It's not too bad, but that's still way more work to set up for a double integration problem to get this thing, I don't know what it would be, like a candle holder as you whirl it around. On the other hand, the shell method, if I want this, shell method, I'm going around the x-axis of rotation. Remember, I want parallel. And automatically you can see if I run this from right to left, now I'm in x, right? So that's nice. I can go from top to bottom to get my h. Right, so x squared plus 1 minus 0, top minus bottom. P, oh, it's just x minus 0. How lovely. And now my volume for the shell would be 2 pi from 0 to 1 x squared plus 1 dx. And this looks a little bit nicer than this. Both should give you the same answer, but one of them is just way easier to do it. So that's where case of the shell method would be preferable. If you know how to do it, you can do it that way. Or you can go back to the disk method. Pontoon, similar thing, but in this case, if you notice, just think about it. I have my function. I'm going around the x-axis, right? And if I'm thinking of a disk method, well, then I have big R. Doesn't look like I have a hole, so I don't need a little r. Whoa. And big R would just be 1 minus x squared over 16, minus 0. However, in this case, if I'm going to do around the x-axis on the shell method, well, now I need to be in terms of y. Solving that guy for y gives you that lovely creature. And now you're just setting up y, and there's going to be a square root in there. And as you think of that integral, that just sounds painful. Versus this integral is actually doable. So for the pontoon case, yeah, you could set up both ways. But why would you make it between two functions when you could just do one function and 0? So in this case, you would want the disk method to set that up. And so you'd end up with v equals pi from -4 to 4, 1 minus x squared over 16 squared dx. If you want to solve that out by hand, it should come out to about 13.4 cubic feet. But I'll let you do that. Last example, sometimes one has to be forced into using one or the other. Because again, as we think about it, if I want to go through this axis of revolution, it's a vertical axis of revolution. If I was doing a disk method, I would need to be in terms of y. So disk would be in dy, which would mean I need to solve this for x. Since it's an x cubed, there's really no way to solve that for x. That's nice and neat. So we can't use the disk method in this case. But what we can do is use the shell method, since that's going to let us be in terms of dx. And in this case, notice your p, since it's over here, it's the axis of revolution minus the variable that we're working in. So right minus left, 2 minus x is p. Height is x cubed plus x plus 1 minus, this line is 1, so you just have x cubed plus x for your height. And you end up with your volume as 2 pi from 0 to 1 on 2 minus x and x cubed plus x dx. If you FOIL it out, turns out something like that. Run an integral over it, go from 0 to 1, and you should end up with 29 pi over 15, which means it is solvable, but you would have to use the shell method for that. So the biggest idea for the shell method is, again, finding p. P is always your variable and your axis of revolution, the difference between the two, right minus left, top minus bottom. H is always the difference between your two functions that you're working with in your given area. And once you have that, it's just 2 pi p times h and whatever variable you're working in, depending on what your axis of revolution. And then from there, you can choose. Be creative with math. You get to decide what you want. So I'll leave it at that. There's some homework problems for you to practice on Thursday. Homework will be due Friday. These are pretty spicy problems. Give them a shot. Try hard, struggle a little bit, and we shall come back on